So I'm going to talk today about geothermal energy and challenges and opportunities that we have. Some parts of my presentations are going to be controversial, and it is part of my professional opinion. Some things may or may not reflect opinion of sage, but there will be happy end. So first, we're going to review what type of geothermal systems are there and why industry is not growing fast. Many of you have heard about dry hot rock and enhanced geothermal system, which are also known as EGS, and we'll discuss why it's so difficult and how need to generate returns, define how you're going to design system, and why parasitic load is so critical and can kill the whole business. And then we'll talk about our alternative to conventional approach, which we call half and puff, and our breakdown technology, and then we'll talk about growing area of this business, which is actually geothermal storage, both mechanical and geothermal. So there are three known ways today how you can generate geothermal power. All 15 or 16 gigawatts global capacity that available today are being generated by the single source, which is conventional hydrothermal. You drill for hot aquifer, you produce it, and then use, depending on the temperature, using one or another technology, either flash cycle or organic ranking cycle or combination, you convert it to electricity. We're going to talk today only about geothermal for the purpose of power generation. So we're not going to talk about district heating or any other application. And so alternatives are, well, you can build downhole heat exchanger potentially, which is called closed loop systems, like radiators, and try to circulate fluid. It will heat up, and then you again bring it to surface and convert to electricity. Or you can try to create artificial downhole reservoir by drilling 2 wells and then fracking between them and then circulating fluid through the open reservoir. Through the fractures, fluid will heat up and then again back and generate electricity. And then I'll explain later on what is SAGE approach and why it is different. So if you look at growth of geothermal industry, it's very disappointing. Okay, for the last 10 years, it's added only 60% of capacity. If you compare with solar or wind, it's like nothing. Plus, only 2% of global resources allow you to produce conventional hydrothermal. It's very geographically limited. And so if you don't live on the ring of fire and don't have volcano under your feet, well, too bad. This resource is simply not available. The rest is hot dry rock. And if we want to convert this growth to exponential growth, which we all want, then we need to figure out how to harvest heat efficiently from hot dry rock. Another problem with the conventional hydrothermal business that it has very high upfront risk profile. And if you look at success rate, it's not very high, or actually it's low. And so from an investment standpoint, it just in general, not an attractive business. There are, of course, exceptions. But can we generate geothermal power from hot, dry rock? And if you live in Texas, let's say, as we do, we all know that there is a very good geothermal gradient. If you drill to 18, 20,000 feet, which we do for deep gas, you're at 200, 230 C or 400, 450 F, which is known to be more than enough to generate geothermal power. And in a recently published Mitchell report, Texas was named as a sleeping giant. There is definitely huge opportunity. Plus, you probably all know that in a good year, we're drilling 20,000 wells, oil and gas wells. So if you assume 3 megawatt per well geothermal, there is a huge opportunity to grow geothermal power. And infrastructure is there. But if you look at projections, okay, where enhanced geothermal systems were supposed to be and where they are now, there is a problem. Because whatever year projection you take was supposed already to produce gigawatts of dry rock geothermal power. And as of now, as of today, we're producing exactly 0. So there is a problem. Projections were made, they're all good, but we're not producing. So why? For the last almost 50 years, people have been trying to implement what is known as enhanced geothermal systems. And as I said, you drilled 2 wells, you frack between them, you circulate fluid, and you convert it. Seems easy. But there are 4 actually challenges, which is, first of all, you need to be able to connect these 2 wells with the fractures. Well, for the last 20 years, we learned how to do it in oil and gas. Then we need to be able to keep fractures either open or at least permeable for the fluid to circulate. And the less permeability, the more friction. The more friction, the more parasitic load. And third is that fluid doesn't want to flow equally through all the fractures. What happens, it tends to find the path of least resistance, erode it, and then temperature goes down, power goes down. So in oil and gas industry, we all deal with the decline rates. Same kind of effect is here, but instead of declining as far as production volumes, it's thermal decline. And thermal decline results in power decline. And to all this to be economical, we need to be able to operate it for decades, not 2-3 years like unconventional wells. It needs to be 20 to 30 years. So there are a lot of challenges. Now, in this presentation, I'm not going to talk about induced seismicity. There is another problem with this system, but I personally believe that it can be addressed, and that is a topic of a separate discussion. So what are the main challenges of hot dry rock geothermal system? Well, I call it power, money, and friction. And I'll explain why, and we'll try to answer, can we solve these challenges? So first, let's take a look at thermodynamics. And if you're sitting on this surface, next to the power plant or next to production injection rate, you really don't care what is happening downhole. Is it closed loop system? Is it open loop system? Whatever it is, the only thing you need a flow meter and temperature gauge, okay? And so you need to measure mass flow rate, and you need to know temperature that working fluid is coming on you, and then you want to cool it as low as possible and re-inject, okay? Now, if you know range of temperature, then all these efficiencies are pretty much known. Of course, you can increase or decrease, be more or less efficient, but it's on the margins. So the point is that usually, if you are in mid-enthalpy space, which is from, let's say, 150 C, which is minimum to be economic, to 250 C, which is probably the limit where we can reliably drill directionally today, maybe even less, then you are in like 8 to 20% efficiency, and everything is given, as I said. You really need flow rate. It's all about flow rates and different in temperature. Now, how you can get flow rate and how you can get hot water depends on what is happening downhole. So these two guys really need to work together to make this system efficiency. But we're doing it not because we actually want money. And the measure how efficient your system is, how you can compare different systems is called levelized cost of electricity. It's actually what is the cost to operate your system. And if you look to the definition, it's very simple. It includes and then you need to take net present value. And let's take an example, okay? Let's say that our utilization is going to be 90%, which is typical for geothermal system. We want to serve 30 years, we'll assume cost of capital at 6%, and we want to generate 3 megawatt, okay? And so what we will also assume that our capex per megawatt, okay, is 7 million, okay? And so, and OPEX is 1 cent per kilowatt hour. We substitute and we find that LCOE is $74 per megawatt hour, or 7 cents, 7.5 cents per kilowatt hour. So if we cannot sell more, well, too bad, then our business loses money. If we're in Germany and guaranteed feed-in tariffs are 21 cents or $200, well, then it's good that we make money. But we can address it differently, because if we want to sign power purchase agreement, it's actually going to fix the price that we're going to be able to sell our electricity for. And so, for example, if we can sell it for 7 cents per kilowatt hour or 8 cents per kilowatt hour, because we know capex, we can calculate what flow rates and what power our system needs to have. So if it is 7 cents, and we will assume that it takes 9 million, which is very optimistic, to drill well to, let's say, 18,000 feet, and we need 2 wells like this, and we assume that cost of organic ranking cycle and all interconnection and everything else is 3 million per megawatt, which is realistic estimate, we immediately can determine that either our wells, 2 wells, can produce 5 megawatts, or we're going to lose money, or in case of 8 cents, they need to produce 4 megawatts, or we're going to lose money. And to do it, we need either 90 kilograms per second flow rate or 70 kilograms per second flow rate. There is nothing else you need to know. Well, the moment you said this, you can easily determine at least what tubing size do you need. And what you find is that if your tubing size is less than 7 inch, everything you generate, you're going to lose on friction. So the whole discussion, can we reuse oil and gas wells? Well, first of all, there is not going to be oil wells going to 200 C. And if it is gas well, most probably, at least in the US, you will have tubing less than 5.5 inch. Well, that simply means that you will not be able to generate more than 1 megawatt per well. And when you substitute this into your cost equations, even if you put drilling well cost to 0, and you do need to complete and do things, you will find that you're always going to lose money, simply because a geothermal is about flow rate. Okay. So what about building downhole heat exchanger, like closed loop system? That is actually very easy to analyze. Now, one thing that we in our company, our philosophy is different from ours. You will hear a lot that you need to avoid depletion for 30 years. That may be very difficult to do. We usually, for our systems, we design it for 10% depletion over 5 years. And then, because I'll be talking about it later, our system is based on fracking, we just need to refract. We don't need to redrill. But for closed loop heat exchanger, let's imagine that you have injector, you have producer, and you have 12 somehow horizontal sections, legs, okay, each 7 kilometers long or 21,000 feet long. I understand that it's impossible to drill, but let's assume. And then you can do heat exchanger analysis of this system and find that if your reservoir was at 250 degrees, okay, then in 5 years, the temperature will drop to 175. And that is assuming that reservoir was initially at 250 and mass flow rate is 90 kilograms per second to get you 3 megawatt electric at the end. Guess what? Even if you can drill it all technically somehow, you can substitute in your LCOE equation realistic estimate of cost of drilling, and based on even most aggressive assumption, it's very difficult to get below 30 cents per kilowatt hour. As I said, even assuming that technology does exist to install all this, okay. let's consider different scenario. Let's drill 2 horizontal wells, 3,000 feet apart, and frac between them. And as I said, let's assume that it's 200 degrees at the bottom. Same assumption on 90 kilograms per second. And we want to generate 3 megawatt. And suddenly the problem becomes very realistic, okay? But we're assuming in this simulation that we somehow magically divided fluid equally. That is okay, but at least, based on this assumption, we can show that A, it's doable, and B, economics looks reasonable. Yeah, it's 9 cents, but we all know that we can, at scale, engineer cost out of it. Nothing bad here, but there is a problem. And the problem is that you have 2 choices. Either your fractures are open, and then you can estimate friction loss between parallel plates. And if you assume that fracture opening is like 3 millimeters, 0.1 of an inch, then it's absolutely negligible. It's absolutely brilliant, okay? Good. Now, let's assume the same and fill our fracture with proppant because we want to remove pressure that takes to open fractures and then circulate through this fracture. Well, that's very bad news because even in a perfect scenario, your friction losses are going to be more than the power lost due to friction is going to be more than you would be able to generate. And even for this proppant, okay, if you look at permeability, it's almost 150 Darcy. So there is no realistic proppant that can allow you to do this. Again, the logic is you want to harvest heat, you need surface area. You need surface area, you need to circulate through this. You need to circulate, you need to keep fractures open. If you cannot keep it open, you need to fill it with proppant. You fill it with proppant, you're killed by pressure loss. And if you look through all the dozen attempts, okay, over the last 40 years to implement EGS, all of them had the same problem. Actually, more than 20 years ago, people correctly calculated what is the minimum impedance should be to be able to generate positive returns. Well, unfortunately, if you look like at Phantom Hill, the actual impedance was 10 times larger. What it means that production was at least 10 times less, under 1 megawatt, than would require to be commercial. Actually, I can make a broader statement. All the attempts, successful attempts, to create EGS systems resulted in power production that is almost 4 or 5 times less that is required to make money. Now, what is the option? Well, if you look at the dependence on fracture opening, fracture propagation pressure, and fracture opening pressure, we all know this curve, okay? We know that this is a fracture initiation pressure, and then there is a fracture propagation pressure, and then there is fracture closing pressure. Well, we don't want to propagate fractures because if we propagate fractures, we're going to lose fluid into formation, and that's going to be our losses. If fracture closed, well, then it will be huge impedance to circulate through these fractures. So this is the window where we need to operate. If we somehow operate in the window between fracture opening and fracture propagation pressure, then there is a chance. Well, actually, if you look at the details on what was done in Fenton Hill, they understood it. The problem was that to achieve this, you need to apply high back pressure. And applying high back pressure requires power. And when this is parasitic load. And so as a result, as I said, the net power becomes negligible. So it all works, except you cannot generate positive outcome. There is an alternative. So imagine now that we do exactly the same. We drill 2 wells, we drill horizontal section, and we create fractures, but we don't connect them. And let me try to show you that I can operate this as a half and part. So I inject in one, I pressurize fractures, and then I produce from another. And then I alternate. So it's like multi-cylinder engine, right? One down, one up, and then this up, this down. Okay, well, let's see what we can do with this. First, let me go back. You need to be able to grow fractures downward. Why? Because if fractures are growing preferentially up, what's going to happen is working fluid, the hot fluid is going to have lower density, and the colder fluid is going to have higher density. So if fractures are growing preferentially up, which they can conventionally do, what's going to happen, all hot fluid is going to go into attic, and all cold fluid is going to go where you need hot fluid. And so you will have very fast thermal depletion. But if you can grow fractures downwards, then this problem doesn't exist. Well, we have this technology. We went to South Texas and we acquired a shell plug and abandon well that was drilled 13 years ago to the depths of 19,000 feet. And it had a 230 degrees C at the bottom. It was dry hole and it was exploratory well. We re-entered it and we did a lot of tests. But first, what we did not re-enter open hole. It was cased with 9.58 up to 11.9, and we cleaned it to 11.5. And so what we first did, we perforated at 79, and we perforated at 11,100, and we were able to create fracture more than 3,000 feet high, okay, going down. And why do we know that we created it? Because we were running tubing, so we could create this fracture through the annulus and then get returns through the tubing. And we had instrumented real-time sensors downhole, so we knew that we are connecting and we were able to circulate through this fracture. Okay, why fractures are growing down? Well, usually in fracking operations, you use density of the fluid, fracking fluid, much less than fracture gradient. And in this case, fractures will grow up, preferentially up. It of course depends on stress regime, but if you have uniform formation, then fractures will grow preferentially up. But if your slurry density is higher than fracture gradient, let's say 18, 20 pounds per gallon, like drilling mud, then losing drilling mud is the same as creating fracture. And this fracture can grow down or will grow down. Well, it's actually a known effect. It's called gravity fractures. It's known in geology, and also Department of Energy developed it in the 60s to bury nuclear waste. So we created this fracture, and we were using 20 pounds per gallon, 21 pounds per gallon fracking fluid, which was actually drilling mud. And we started to circulate. But of course, to open and circulate, as we discussed before, due to the friction, we're losing more than 30% of the fluid into formation because we could not keep our pressure below fracture propagation. And then we shut in, and when we opened, all the fluid came back. And so what we realized that we actually can operate this fracture as a half and puff. We can pump in, inflate fracture, and then it will flow back with the pressure. Well, we simulated it. And what we found is that because when we inject cold fluid, and remember, opening of the fracture, if you simulate it, is like 0.1, maybe 0.2 of an inch. And it has, as I said, 3,000 feet height and maybe 200, 300 feet width. And when we inject fluids, cold fluid into it, it acts as if you have two hot plates. The cold fluid drops down and it's substituted almost immediately by a hot fluid. We use a pad. So if I need to circulate, let's say 20,000 barrels a day, I'll pre-stress my fracture. I'll put initially maybe 100,000 barrels the fluid. And so I will operate it on a delta, small delta, like 1/5 of the total volume. So it behaves like an air mattress. I keep it always pressurized, okay, above fracture closure. I never allow this fracture to close. And so I operated between fracture opening and fracture propagation pressure, and it allows me to maintain the desired temperature when I need it. It heats very fast. Yeah, it takes time for fluid to replace water, the well volume, but it may take 15, 20 minutes to do it. So if I have multiple wells, I can circulate it. I can operate it, as I said, as a multi-cylinder engine. Well, there is another opportunity. So because in this well we were perforated, our temperature were really reasonably small. What we realized that we can operate the system as a mechanical storage. So you pump in and then you produce, and you put mechanical turbine like Pelton turbine, and you can convert it to electricity. And we tested efficiency, and downhole efficiency was like around 90%, which gives round trip efficiency 70%, which is very good. It's actually very competitive with pump storage hydro, which is 95% of all global storage capacity. But if there is a good geothermal gradient, then what you do, you add heat exchanger and you harvest heat from the hot fluid that is flowing back. And now your efficiency becomes not 70%, but 200%. Well, it's not really efficiency 200%. Efficiency is still 70%, but you harvest additional heat. And you can actually operate it as a storage, which produces more power than you store, or you can circulate it, operate it as a geothermal baseload, because you can operate it, as I said, as a multi-cylinder engine. So we set it up and we did 6 months of testing, validating different regimes. And what we found is we can charge for 8 hours and produce for 16 hours. Why 816? Well, because if you power it with a solar that is up 8 hours, and then you produce 16 hours, then it gives you 24 hours. So now in combination between solar and geothermal storage, it gives you base load, or you can do actually load following, because instead of releasing everything in 16 hours, you can release everything in 2 hours. Why do I want to release everything in 2 hours? Because if you are, let's say, in unregulated grid environment like Texas in summer, then the prices in the afternoon, instead of being 4 or 5 cents per kilowatt hour, will be 20, 30 cents per kilowatt hour. There is tremendous arbitrage opportunity. And also you can use it as a peaker power. So how it works? Well, you have a well with horizontal section and several fractures. You have a pump and turbine, and then you have motor and generator. So if you have 2 wells, you can do it in and out. And as I said, if you have a good geothermal gradient, you put a heat exchanger and let's say organic ranking cycle, and then you generate additional electricity. So how it can be scaled up? Well, you can drill several wells. As I said, our today vision is that it's very practical to assume 3 megawatt per well. So if you want, let's say, generate 50 megawatts, then you would pad drill 20 wells, and that's going to give you 50 megawatts facility. And you can do pad drilling, so footprint is going to be very little. It's like 10 feet at the surface between wellheads, and it's going to be 2 rows, and so it's going to be very compact. Or there is opportunity to use, we in all our applications right now are designing for 4 or 5 wells, 4 or 5 fractures per well, but there is ability, of course, to increase number of fractures, and if it's always competition between larger casing size or tubing size, as I said before, and number of fractures, you want to increase flow rate and increase your power generation. But we have a software that allows to optimize all this. And as I said, you have a plenty downhole space to directionally position this fracture. Needs to be 200 feet apart, not to thermally affect each other in 30 years. Thermal conductivity of rock is very, very low. So the drawback is it's very difficult to harvest heat because you cool fast, but also fractures or wells don't thermally affect each other if there is a very small separation. And so on a scale of 1, you can build it today. We can build it at 6-8 million per megawatt, which gives you LCOE in a range of like 8 to 9 cents. But at scale, we can easily reduce it to 3-4 cents per kilowatt hour, which has become enormously cost competitive. That is if you use it as a base load, but if you use it as a storage, then it is actually cost competitive with all other potential energy storages, because really there is nothing today available as a storage in a space between 4 hours and maybe day or lower days, except hydro pump storage. Well, hydro pump storage, you're not going to build at 3 megawatt capacity. It's usually hundreds of megawatts. And also you really need to be in a mountain area, because otherwise you will not be able to build it. But from a physical standpoint, there is no much difference between pumping up, pumping down, and the highest pump storage is built in Chile. It's like 1 kilometer or 3,000 feet high. As you know, we can easily drill to 15,000 feet, and that is going to be like 5 times higher energy density or lower footprint than pump storage. And it can be implemented on any scale from 3 megawatt to 100 megawatts. Very scalable and very dispatchable. So let me give you an example of how it can be implemented. We'll consider a California grid. And the problem with California grid that it was successfully greened already from 6 a.m. to 6 p.m. But then what is happening when sun is not up? Well, then we need somehow to green this duck curve. And so what we're going to do, we can add 7 gigawatts to totally green it during day hours. Then we'll add geothermal storage with 14 gigawatts to green it during night hours when sun is not up. And then we'll still use lithium-ion batteries to add 2 gigawatts to compensate for some peaks where short-term geothermal storage becomes inefficient. If you put all the numbers together, suddenly it's very manageable task, and it takes only 15 billion. It may sound like a big number, but it's not, because everything else, when you look at greening the grid, you're talking about trillions of dollars. So that is the success, vision of success, and I'll open it for questions.
Thank you, Lev, for the presentation. Before we move ahead with the questions, we have a few in the chat. I just want to remind everybody for the next technology webinar on June 22, Quais Energy. So please check our website, SPE Connect, LinkedIn, Twitter to find more information. Lev, one of the first questions we have here, and I'm going to go probably from the last to the first one, is from Mark McClure. So yeah, the thermal storage idea sounds quite interesting, but the question is, why don't do it in kind of a cheaper way, in vertical wells, sedimentary reservoirs? Why the approach in a more kind of fracturing style in tight reservoirs?
The answer to this question, you can do it differently, but if you want to maximize power, then or round trip efficiency, then playing with the fracture closure pressure, okay, is optimum for what we're doing, okay? I'm not saying that is the only way to do it, but we found through the modeling that if we want to optimize storage capacity, that's what results in optimization of the storage capacity. And another point is that mechanical way of recovering mechanical power, like Pelton turbines, are the most efficient, okay? So Pelton turbine that we're using, they provide up to 90%, 95% efficiency. So it's all combination of efficiency and cost per megawatt.
Thank you, Lev.
But there are other technical opportunities.
Thank you, Lev. Hope we answered the question from Mark. If there is a follow-up question, feel free to kind of post it in the chat. Next question, from an LOC perspective, will you consider the Sage model more economical than traditional advanced geothermal closed loop or EGS enhanced geothermal system? Is that the conclusion for you, Lev?
I don't like to compare abbreviation. And so what is true, we consider our approach to be very efficient. I don't want to claim that there are no other approaches that cannot be safe or high efficiency. I don't believe that closed loop downhole heat exchangers can compete for power generation with other approaches.
Thank you, Lev.
Economic standpoint, technically it's doable, but not economically.
Perfect. Next question. Can the Sage geotechnology be a standalone without relying on any other renewable power, such as solar?
The answer is yes. As I said, we can operate our system as a multi-cylinder engine, and we don't need any other source of energy.
Perfect. Thank you, Lev. I think there's another question from Josh. Great presentation. In Europe, they need to drill, they need to get temperatures above 100 degrees Celsius. It's a very heterogeneous system, which requires multiple casing settings in order to reduce the cost. Any comments about that particular case when you need to run multiple casings in order to get to the depth where you get the heat?
Well, that's how we came with idea of mechanical storage. So if you cannot reach, again, it's my opinion, but if you cannot reach at least 150 C at a reasonable drilling cost, then it's just not going to be economical, okay? But and then it's just not a good application of baseload geothermal system. You need to have area with good geothermal gradient. If it's not, then mechanical storage can be done pretty much at any depth. The higher permeability, the higher your losses, but other than that, it can be done anywhere.
Thank you, Lev. I think we are going to continue in social media to keep the records for the questions. We appreciate your time today. I know you have a board meeting, so good luck with that one as well.
Thank you. Appreciate. Thank you very much. Bye.
Thank you. Thank you, everybody. We look forward to seeing everybody in the next new technology webinar, SPE Geothermal Technical section. Have a good one. Have a great week.